the center, but I want to talk about a little bit technical with a case study because I work long with academia industry altogether. So okay. So I belong from the Transparent Ocean Group, and Professor Jinchen Ren lead that part. And our group actually goes with different types of research and modality for the data-driven analysis, but which I mostly handle that acoustic emission-based analysis. So what are my objective of this presentation is kind of a little bit wider look if we go through that in the subsea structure, infrastructure, there are a lot of pipelines on the ground and under the ground as well. So in this realm, actually, acoustic emission-based sensor can be used to identify the failure very faster, actually, and this is non-destructive. And how this acoustic emission testing works, and what would be the limitation, and how AI can solve. To talk about those two is when we, as a researcher or from the academia, like intend to jump to the artificial intelligence based model, the problem comes is we need kind of data which has been leveled properly, right? So the level should be like whether it is a faulty situation or not, or maybe there is any leak occurring is going there or not. So for that we need industry experts or human experts, domain experts to annotate that part. You cannot just cut off the traditional approaches because unless or until you can validate those data and pass to feed forward this to that memory-based models like the universal approximators. So can we make easier that part to help that part to make that type of data without spending a lot of time to make the simulations or maybe the testing bed preparing those things and create that type of artificial leaks or some kind of phenomena to train that model and get a result. So a little bit of A inspection history I want to go through. Everybody knows this thing, but a little bit of thing is like when in 6500 BC, when the potters used to do this pottery work, if there was a crack in that vessel or this kind of thing, they used to just put, and this kind of sound comes from that. So by listening to that sounds, they used to understand like, okay, yeah, there is some kind of cracks or not. And then what happened is this progressed very slowly, and we have seen these metal workers, and they use this type of listening power to understand if there is any bending problem or issues like these elements, right? But things got little bit interesting when German Joseph Kaiser actually started inspecting this phenomena, and he actually doing research with this material has certain type of memory inside of it. So from that time, actually from 1900, we see a lot of transitions into the industry for this acoustic emission-based inspection. So actually what happened that in this material, we all have memories, right? So we remember about the past. So if you have any hurting in your body, or if this metal has some kind of problems in it, so with the acoustic emission, we can actually understand that by attaching the sensor to the object or pipes or whatever. So now the question comes like, what produces the acoustic emissions? First of all, in the material, there is like crack propagation definitely, and that created some kind of impacts on the particles. So that creates some kind of like distortion, and this distortion can be heard or listened from the sensor. Definitely the cracks. Okay, this part is really interesting. So any kind of chemical process changes, if going through on this material, this thing also can be detected, but this is very difficult. Corrosion might be one point, and we actually experimented with the corrosion data and it works pretty well, but there are challenges as well. Also, definitely that friction and fretting, and that turbulent flow. Yeah. So what happened is the fluid or any kind of things, if you pass through the very pipes, especially, that doesn't create any kind of leak information on that. But that kind of, when you pass something, there is certain pressure or certain type of waveforms that actually, that chaotic movement that actually help us to understand whether anything is wrong there or not. So how does A testing work? It's pretty simple actually. So we attach the sensor to the body of the pipe maybe, or any material. I'm talking about the pipeline system, so I'm mentioning about the pipe. By the way, A stands for acoustic emission, yeah. And we collected the signals and digitized this to the system monitor, the computer, and actually with that we kind of see some kind of waveforms, and the waveforms, the experts look at it and they give us some kind of results like, yeah, there is a problem going over there, or there is not. This is non-invasive technique. Early detection is possible, as I mentioned already. And so what happened, this type of signals have been captured from these sensors, and you see here kind of event I mentioned over there. So these we call events, acoustic events. So what are those? These are kind of phenomena. If any that type of problem happened, or this type of memories are in this material, so we could capture that one. Okay. But what happened in earlier days, now computers are there, we can like understand what type of thresholding we have to do, because certain part we don't interested, certain part we're interested. So earlier days, what people used to do, or researchers used to do, they printed out this thing and draw a line on top of that. But now we, thanks to this modern system, we can do it pretty cleverly and improve the things better. However, there is challenges, because that's the theory. In real time, sometimes like this, the second picture, and we try to understand these peaks from there. And these peaks or this burst we want to understand, because to understand what type of leakage are there or not. Okay, but what were the challenges actually? Number one challenge, limited data availability, because as an academia, when I did my PhD, it was very problematic to get this data open source. So what we did, we had our own experimental test bed, and we worked with the companies and set our test bed and collected data, and we did that analysis. And if you look through that existing publications, mostly as there is not that much data availability, those CVD simulation based research we get into this research based domain, the publications, but data driven analysis in this domain are very limited. But we are lucky to be a part of the journey into this giant team, so publishing a lot of publications on top of that. So today I will present one of our case studies which might give some insight how would we help for this purpose with data driven analysis. So what happened here, I'll present one case study actually. So this is the simulation test bed we produced, we actually developed like the real industry. And here I'm not going into further very detail, because I mentioned into the source links. You can go to the publication and check the details of the experimental test bed, or you may talk to me as well. So here actually we kept two sensors We are calling channel 1 and 2. The purpose was keeping two sensors from that acoustic emission sensors, because we try to understand and correlate the information gathered from both of the sensors altogether, because acoustic emission has these challenges. You cannot tell the location exactly, but you can tell whether there is a problem or not. So this type of simulated case study actually can help us to understand, like with two sensors, can we make some decisions, or can we give some modality based decision or channel wise decision that might help us to improve the performance. But in the AI based system, actually we may jump and say, okay, we collect the data, we know this is the simulation based thing, and just throw to the model, and model will give you, okay, this is A and this is B, there is leak or not. But you understand this type of data to collect from this thing, it's a lot of expenses going on and a lot of fundings needed to be done, and we need to create a lot type of leak on these pipes to get different types of signals. So here what we did is we actually generated three types of leaks: 0.3 millimeter, 0.7 millimeter, and 1 millimeter. And we also generated several types of pressures to understand what type of signal we might get. You see, previously I talked about this burst, right? So those bursts actually ideally looks like this, and people extract the features from there. And if we go to that non-destructive testing AI-based guidelines, they talk about certain statistical features. They talk about this thing as like AE features. This is statistical things. However, this thing actually does not help us in this study, because we try to simulate the real world and try to understand how this can happen. So you see, this is 0.3 millimeter and 0.7 millimeter data set. So those are the normal signal, and we increase the leak size actually 0.3 and 0.5, 1 millimeter. You see how the signal changes from the time domain. Okay, it's very. And now what we did, we actually extracted that guided features, what they mentioned into their textbook or the guidebook, and this is what we got. It doesn't help. It helped us with the CFD-based simulation, because when we did the simulation, we actually got pretty good result. But when this thing we did, not. So later, what we thought, okay, maybe manually we could do this thing. However, let's dig dive. So we actually proposed on top of those features, we tried to calculate the empirical cumulative distribution function. I'm not going into that much technical. Something we calculated from there. And what happened with two samples actually we took, one from normal, one from abnormal. And we tried to understand this cumulative distribution things from there. So what happened, you see, when there was any leakage and when there is normal, there is a gap, certain gap in these places. So we calculated that gap from there, and we called it part-line leak indicator, PLI. So now what we got after that? We plotted that indicator over there, and you see it's very clear for each of the cases, for each of those guided features now, and really separable with the bare eye. We can see that. So how did it help us? So previously actually we spent a lot of time to simulate a lot of type of faults by pencil lead brake test or any other test as possible, to understand the signal, look at those, trying to understand the mechanical properties of the thing. But with our proposed approach, what we saw in this real-time test bed, just with plug with this and with two samples, we can actually now level the data. Kind of, it's very generic way, right? So peak or this kind of things. So for 0.5 millimeter and 1 millimeter, for all the guided features which has been guided by non-destructive testing books, we checked our method on top of that. So pretty much every time we are getting kind of very good separation. Though right now a lot other machine learning techniques might help us which one is the best or which one is not. Yeah. Again this. Now at the end, I want to show like we tried with the comparison of different most popular values which have been suggested from a lot of literatures we have gone through, but we felt like ours one was helping us a lot. But yeah, what happened? We did this thing, so what, right? This is the final thing actually. So what happened now, you do not need to spend time on leveling the data, because when from this industry, unless the images come, right, the signal comes. The problem is which one would be the defective signals or which one is not the defective signals. It is very time consuming to understand, unlike images, because in the image we can see, we can like experts say, okay, this is this is that. Here's the case is completely different. So now we can actually train a deep learning model or whatsoever, and we can actually train it, right? So then back to that thing for Joseph Kaiser. So he mentioned a inspection was kind of a memory-based inspection. Memory was there in the particle, right? Material, okay? So definitely here our deep learning model is kind of a memory, is working like that again, because what we learn from that thing, we can now pass those knowledge to this algorithm. Now, if any different data comes, what will happen? Do we need to train it from the beginning? No, because we already justified our model with certain type of things. So we can actually start training after that. So you do not need to train every time this thing. So we are actually gradually building this memory system. Maybe from different vendors they are coming, they are telling us these are our signals. So let's see how this memory is accumulating to which direction, because in the image processing part or this type of AI text to generation part, what you see today is memory-based learning or something like artificially clever there, because we people give them the data. We people available everything on the Google. We people available images to the Google, so they can learn from there and they can give us the prediction, but industry cases are not. So yeah, and the purpose here is like to demonstrate one of our expertise so that we can help on this entity-based system to make a prompt decision. There like this would help them. And if you need further information related that, you can check always the paper or drop me an email so I can share it or research work. And let's thank you.